Hello students. So here in this video today, we are going to talk about fundamental concepts in organic reaction mechanism. And majorly here, we will be talking about reaction intermediates. Now you must be wondering, what is reaction mechanism? So reaction mechanism is basically the sequential account of each step that describes the movement of electrons, the energy that is required during bond formation as well as bond cleavage, and also the rates of transformation of reactants to products. So this is known as the reaction mechanism. Alright then, let's look at the learning objectives here for the video. So today we will be talking about the types of cleavage of covalent bond, and we will be looking at what is reaction intermediate and how many types of reaction intermediates do we have. So let's just first understand what happens in an organic chemical reaction. So we have two substances here, which are substrate and this is reagent. Now, the substrate is a molecule which is being attacked in a chemical reaction, and reagent is going to be the molecule that is going to act as attacking species. It means this reagent is going to attack on the substrate. Now, this reagent can be electron deficient and it can also be electron rich. Alright, so if this reagent is electron deficient, then the substrate should be electron rich. And if this reagent is electron rich, then in that case, substrate should be electron deficient. And why so? Because we know in any chemical reaction, any substance wants to satisfy its octet, right? Because it wants to attain stability. So each chemical species in the chemical reaction tries to satisfy its octet. That is, it wants to have a set of 8 electrons. So the electron deficient species, which are electron seeking, are always in search of electrons. Alright, and electron rich species, as the name suggests, has a lot of electrons and it is going to always attack a species which wants the electrons. That is electron deficient species. So when the substrate and this reagent, they're allowed to react, what happens? An intermediate product is formed. And this very product that is formed is short-lived. Basically, this short-lived species forms before the formation of final product. So a reaction passes through the formation of many intermediate products, but the final product will be formed from the most stable intermediate. So the intermediate that will be formed during the course of reaction has to be stable. Why stable? Because then only this reaction is going to lead to the formation of final product. So out of many possible intermediate products, the final product will be formed from the most stable intermediate product. So substrate and reagent react to form intermediate, and only the stable product will lead to the formation of final product of the reaction. Now we just learned about attacking reagents. Now in the reaction, the attacking reagents can be electron deficient or electron rich. So when the attacking reagent is electron deficient, it is known as electrophile, and when the attacking reagent is rich in electrons, it is said to be a nucleophile. And the intermediate product that is formed during the course of reaction are known as reaction intermediates. And let me just make you recall this, that which reaction intermediate is going to lead to the formation of final product? Only the most stable species is going to give you the final product. So this was a brief introduction to make you understand what exactly happens in an organic chemical reaction. And what are we going to actually talk about in detail today? We're going to look at these reaction intermediates, which are carbocations, carbanions, free radicals, and carbenes. But before we get into the details of the types of reaction intermediates, let us just first understand what kind of cleavage can take place in a covalent bond. So let's start with the types of cleavage of covalent bond. So you know what is a covalent bond? Chemical process that involves basically the breaking of older bonds of the reactants that leads to the formation of new bonds in the products. Alright, so generally in the organic chemistry, the breakage of bonds is referred to as cleavage or fission of a covalent bond. Alright, so whenever a bond between two atoms it breaks, it is known as the cleavage of a covalent bond. So there are mainly two ways for the cleavage of the covalent bond in organic chemistry, and those two ways are homolytic cleavage and heterolytic cleavage. So let's first take a look at homolytic cleavage, or we can say homolytic fission. So consider a covalent bond that is present between two atoms. So here we can see we have two atoms and a covalent bond is formed between these two atoms. And if you closely observe here, then you can see that the bond formation that takes place between these two atoms, they are identical. It means they have the same electronegativity. So this shared pair of electrons is concentrated in the center because the electronegativity is same. So the electron density is not going to get pulled towards in any of these atoms. Rather, it will be concentrated in the center of these two atoms. So when this bond is broken, what happens? Each atom will take away one electron towards itself. So this is known as homolytic fission. That is, when the bond gets cleaved, what happens? The atom takes one electron each towards itself. And this results in the formation of what we can see as free radicals. So what did we see here? We saw in the case of homolytic fission, the electron density is concentrated in the center of the atom and each atom takes away its share. That is, it takes away one electron and leads to the formation of free radicals. So here let's take a look at the example. So here we have a molecule of chlorine, and in the presence of light, homolytic cleavage takes place, leading to the formation of chlorine-free radicals. Now let's take a look at the heterolytic fission. Now heterolytic cleavage basically involves breaking of a molecule so that the two electrons that exist in a covalent bond are retained with only one atom of the molecule. So this in turn leads to the formation of a cation and an anion. A cation will be the one that is deficient in electrons, and the anion is going to be the one that is rich in electrons. So that is why a cation acquires a positive charge, whereas an anion acquires a negative charge. The unequal distribution of the shared pair of electrons takes place during this type of cleavage. So let's see the two types. So in the type 1, we can see if the bond is cleaved towards B. Now, why does this happen? Why is the bond getting cleaved towards B? It is because it is assumed here that the atom B has more electronegativity, right? And we know that an electronegative atom has the tendency to pull the shared pair of electrons towards itself. So that is why the electron density that is concentrated here will be moved, or we can say it will be shifted towards more electronegative atom, that is this very atom B. And that is why this results in the formation of what we can see here as B minus. That means an anion of atom B is formed, and the atom A, which has got no electrons. Why? Because the electron density got shifted towards the more electronegative atom B, acquires a positive charge. So that is why the cation of atom A is formed, which is A plus. Alright. Now let's take a look at the type 2. So what happens here in this molecule? Let's assume that the electronegativity of atom A is more. Now what will happen? This shared pair will be shifted more towards this atom, that is atom A. So what is going to happen? So the heterolytic cleavage of this very bond is going to result in the formation of A minus anion and B plus cation. So this was all about heterolytic fission. So now we know that how a covalent bond can be cleaved, right? It can be cleaved either through homolytic fission that majorly happens in the presence of sunlight, as well as the bond can be cleaved through heterolytic fission. And here in this case, always remember that the more electronegative atom is going to take away the shared pair of electrons, resulting in the formation of ionic species. Now in the beginning of the video, we were introduced to the concept of reaction mechanism, where we saw that when a substrate is allowed to react with a reagent, that is the attacking species, what gets formed? A short-lived species are formed, right? And in those short-lived species, only that very species is going to lead to the formation of final product, which is more stable. All right. Now let's take a look at the types of reaction intermediates. Now we know there are many organic reactions that do not proceed in a single step, but they take several steps to form the final product. Alright, now when there is this case of multiple steps reaction, what happens during the course of reaction, a short-lived species can be generated immediately into the other intermediate or reactants or products or side products. So this type of short-lived species is known as intermediates. So always remember that during the course of reaction, when such short-lived species are formed, they are termed as reaction intermediates. Now these intermediates, they are highly reactive, so they cannot be isolated. But many theoretical and experimental methods have proved their existence and structure. Now, today we are going to look at many reaction intermediates which are based on carbon. We're going to look at free radical, carbocation, carbanion, and carbene. So let's begin with free radical. Now we know that free radicals are one of the reaction intermediates that are formed due to the homolytic cleavage of the covalent bond. As we can see here, so this is the bond, and both these atoms that are participating in this reaction take one electron each, and this is known as homolytic cleavage. So here we can see that now they contain an unpaired electron having an incomplete octet configuration with even electrons. So here we saw how this chloromethane molecule undergoes homolytic cleavage to give methyl free radical, which is this radical, and chlorine free radical, which is this one. And these free radicals, they are highly reactive and they're neutral. Now here we can see that in the free radical, this carbon is sp2 hybridized. Alright, and its shape, as we can see, is trigonal planar with 120-degree bond angle. Okay, now there are three sp2 hybrid orbitals that are going to form sigma bonds by overlapping with this 1s orbital of each of these hydrogen atoms, and this gives us 3 sigma CH bonds. Alright, now what is left? One unhybridized 2p orbital is left, okay, and that is perpendicular to the plane of these 3 sigma bonds, as we can see here. Now this unhybridized p orbital, it has got an odd electron, as we can see here. So we know this is going to be paramagnetic. Why paramagnetic? Because it has got one unpaired electron. So now let us take a look at the stability of carbon free radicals. Now the stability of carbon free radical, it can be described by the plus M effect, which is the mesomeric effect, the resonance, hyperconjugation, and inductive effect. We have learned all of these electron displacement effects in detail in our previous lecture. Now let's look here at the effect of hyperconjugation on carbon free radicals. Now before moving ahead, what is hyperconjugation? Let us just revise. So hyperconjugation, we know, is the delocalization of sigma electrons of CH bond of an alkyl group into the pi star orbital or p orbital, and this is known as hyperconjugation effect. It is a permanent effect, okay, and this is also known as non-bond resonance. So hyperconjugation, we know, is directly proportional to the number of alpha hydrogen, okay. The greater will be the number of alpha hydrogen, the greater will be the number of hyperconjugation sets or structures. The greater the hyperconjugation structures, the greater will be the stability of the carbon free radical. Okay, we know this already. Now, let us just revise few things. The number of possible hyperconjugation structures will be given by number of alpha hydrogen plus 1. So, let us take a look at the free radicals that are given here. So, here we have got methyl free radical, primary free radical, secondary free radical, and tertiary free radical. Now, you have to see which free radical is going to be most stable. Now you know the stability of free radical is directly proportional to the number of hyperconjugation structures. The greater the number of hyperconjugation structures for a species, the greater will be its stability. Right, and we know the greater number of hyperconjugation structures are possible only if the species has greater number of alpha hydrogen. Okay, so here in the 4 free radicals that you see, which of these has a greatest number of alpha hydrogen? So we can see here this tertiary hydrogen, it has got how many alpha hydrogen? 1, 2, 3, 4, 5, 6, 7, 8 and 9. So it has got 9 alpha hydrogen, and thus we are going to get how many number of possible hyperconjugation structures? 9 plus 1, that is 10. Okay, so this is the example of tertiary butyl free radical, where we can see we have got 9 alpha hydrogen, and greater the number of alpha hydrogen, greater will be the number of hyperconjugation structures that will be formed, and thus greater will be the stability of the free radical. So tertiary free radical is going to be the most stable, and then the secondary free radical will be stable. Why? Because it has got 6 alpha hydrogen, as we can see here. So this is the secondary free radical, which is the isopropyl free radical, and here we can see it has got 1, 2, 3, 4, 5 and 6. So there are 6 alpha hydrogen, and it means the number of possible hyperconjugation structures will be 6 plus 1, that is 7. So after tertiary free radical, secondary free radical is going to be stable, and then the primary free radical will be there when you talk about the stability order. Why? Because it has got more number of alpha hydrogen if you compare with the methyl free radical. In the primary free radical, we can see there are 3 alpha hydrogen. Okay, and so it is going to have how many number of possible hyperconjugation structures? There are going to be 3 plus 1, that is 4 hyperconjugation structures. And lastly, we are going to have methyl free radical. It does not have any alpha hydrogen, as we can see here. So there is going to be no hyperconjugation structure for methyl free radical. And so the order of stability for these carbon free radicals is going to be 3 degree, followed by 2 degree, then 1 degree, and then the methyl free radical. So tertiary free radical is going to be most stable. Now if you look here, you can see that there is delocalization of electrons of this sigma CH bond with this p orbital of this carbon atom. So likewise, this delocalization of sigma electrons of CH bond of the alkyl group is going to take place into the p orbital here, and this is going to give us 9 similar hyperconjugation structures. So that is why tertiary free radical is the most stable, because it has got the greater number of alpha hydrogen, which is going to give us greater number of hyperconjugation structures that is going to stabilize this free radical maximum. Now, do you know free radical can also assume the pyramidal shape, because the energy difference between the pyramidal and planar shape is not much. For example, bridgehead free radicals, they are pyramidal. Why? Because they cannot assume the planar geometry, because it has got the angle strain in it. So that is why they are pyramidal. And the free radicals where carbon is connected to highly electronegative atoms, they are also pyramidal. For example, CF3. So free radicals can assume the pyramidal shape as well. Now let's talk about another reaction intermediate, which is carbocation. Now, what are carbocations? Now, the chemical species having a positive charge on carbon and carrying 6 electrons in its valence shell, those species are termed as carbocations, carbenium ions, or carbonium ions. So, let's see how they are formed. So, this is a molecule of chloromethane. Now, what happens here? This bond, that is the sigma bond between C and Cl, undergoes heterolytic cleavage, where the bonded pair of electrons are moved towards chlorine, and chlorine becomes chloride ion because it takes up the 2 electrons and acquires a negative charge, and what is left behind is the methyl cation. Now as we can see here clearly that this is the methyl cation where the carbon atom has the positive charge. Alright, so the reaction can be written here like this: CH3Cl undergoes heterolytic cleavage to give you the methyl cation, which is of course the carbocation, and along with that you get chloride ion. So this is how the methyl cation looks like. Now let's talk about the structure of this carbocation. So we can see here the carbon atom is sp2 hybridized, Its shape you can see is trigonal planar with a bond angle of 120 degree. Now there are 3 sp2 hybrid orbitals that are going to overlap over the 1s orbitals of each of this hydrogen atom, leading to the formation of 3 sigma bonds. So these CH bonds that you see are the sigma bonds. Okay, and what is left behind? The carbon is left behind with an unhybridized 2p orbital, as we can see here. And this is perpendicular to the plane of the 3 sigma bonds. Okay, so this is how the structure of methyl cation looks like. Let's talk about the stability of carbocation. Now, the stability of carbocation can also be described by the plus M effect, resonance, hyperconjugation, and inductive effect. Now, let's see the effect of hyperconjugation on carbocation. Now, as we learned, hyperconjugation is directly proportional to the number of alpha hydrogen. The greater will be the number of alpha hydrogen, the greater will be the hyperconjugation structures, which is going to stabilize the carbocation more. So, that very carbocation which has got a more number of hyperconjugation structures is going to be the most stable. So, here we can see which of the carbocation has got a maximum number of alpha hydrogen. Of course, it is going to be the tertiary carbocation, right? So, this tertiary carbocation contains 9 alpha hydrogen, okay? This is the third butyl carbocation, and there are 9 alpha hydrogen, as we can see here. So, what happens here? There is the delocalization of sigma electrons of CH bond into the p orbital of this carbocation, okay? So, as we can see here, the sigma electrons of the CH bond, they are delocalized into this p orbital of this carbocation. And likewise, the similar thing is going to happen with the other 8 CH bonds. So, the delocalization of sigma electrons of these 8 CH bonds is going to take place with this carbocation, and it will give us 9 similar hyperconjugation structures. So, if you talk about the stability order, so tertiary carbocation is of course going to be most stable, followed by secondary carbocation, then primary, and then the methyl cation. Let's take a look at the secondary carbocation. So here we can see it has got 6 alpha hydrogen. This is the isopropyl carbocation, which is the secondary carbocation, and it has got 1, 2, 3, 4, 5 and 6 alpha hydrogen. So that means it is going to have how many number of possible hyperconjugation structures? 6 plus 1, that is 7. So there are total 7 hyperconjugation structures possible for secondary carbocation. And for primary carbocation, we can see it has got 3 alpha hydrogen. So how many total number of hyperconjugation structures are possible? 3 plus 1, that is 4. So primary carbocation is going to have 4 number of total hyperconjugation structure. The sigma electrons of the CH bond, they are delocalized in the p orbital of this carbocation, as we can see. Likewise, the delocalization of sigma electrons of another CH bond will take place. And when the delocalization takes place like this in the p orbital of the carbocation, so we get total 4 number of hyperconjugation sets. And then we have methyl carbocation, which we know does not have any alpha hydrogen. It has got no hyperconjugation structure. So that is why methyl carbocation is going to be the least stable among these. So tertiary carbocation has got most number of alpha hydrogen, so it is going to have more number of hyperconjugation structures, which is going to account for its maximum stability. So, do you know the stability of carbocation can be determined by the following? Now, stability of carbocation is directly proportional to plus I upon minus I. Then the stability of carbocation is directly proportional to plus M by minus M. Stability of carbocation is directly proportional to resonance, and stability of carbocation is also directly proportional to hyperconjugation. But when you talk about the order of stability, the priority order is first the plus M effect will be considered, then the resonance, then the hyperconjugation, and lastly the inductive effect, that is the plus I effect. Let's talk about another reaction intermediate, which is carbanion. Now, as the name suggests, this chemical species is going to have a negative charge on the carbon, and hence the name carbanion. Now, this species, it has got 8 electrons in its valence shell. So how is it produced? So take this example of a chloromethane molecule. Now what basically happens, it is produced due to the heterolytic cleavage of the covalent bond, where the shared pair of electrons remains with the carbon atom and chlorine cation is formed. So what do we get when the heterolytic cleavage of this bond, that is CCl bond, takes place in chloromethane? We get methyl anion when the shared pair of electrons moves in towards the side of carbon, and we get methyl anion and chlorine cation. Now, when you talk about the structure of carbanion, which is methyl anion here, we can see that the carbon atom is sp3 hybridized, okay? And its shape is pyramidal, as we can see here. Now, we have got 4 sp3 hybrid orbitals, where 3 out of 4 sp3 hybridized orbitals, they form sigma bonds with 1s orbital of hydrogen atom. And what is left? One hybridized sp3 orbital is left that is going to contain the lone pair of electrons, okay? So as we can see here, this hybridized sp3 orbital, it has the lone pair of electrons, okay? So this is how the structure of carbanion looks like. Let's talk about the stability of carbanion. Now the stability of carbanion can be described by -m effect, resonance, S character and inductive effect. Now here we are going to take a look at the inductive effect on carbanion. Now we know an alkyl group has a +I effect, that is electron donating effect. So whenever an alkyl group is attached to a negatively charged carbon atom, we know what is going to happen. Since the alkyl group has +I effect, that is, it is going to donate the electron to the negatively charged carbon atom. So the alkyl group, it has got a tendency to push the shared pair of electrons towards that negatively charged carbon. And what is going to happen? The intensity of the negative charge is going to increase on the carbon atom. Why? Because the alkyl group is giving away the electrons to that negatively charged carbon atom. So the intensity of the negative charge is of course going to increase. And in that case, the carbon atom is going to get destabilized. Okay, because it cannot hold that much of a negative charge. It wants to get stabilized, but the alkyl group is pushing more electrons to that already negatively charged carbon atom. So we can say that the stability of carbanion is inversely proportional to the number of alkyl groups that are attached to the carbon atom. Because more the number of alkyl groups, lesser will be the stability of the carbanion. So there is an inverse relationship between these two. So we have 4 carbon ions on our screen, and can we now determine the stability order? Yes, of course we can, because we now know that the higher the number of alkyl groups, lower is going to be the stability of the carbon ion. So here we can see that methyl anion, as we can see, does not have any alkyl group, as we can see here in the structure. And hence it is the most stable carbanion. Why? Because when there are no alkyl groups attached, there will be no -I effect. That is, the negative charge won't be intensified any further, and thus it will be the most stable carbanion when you compare this with primary, secondary or tertiary carbanion. Then you have primary carbanion. Now in the primary carbanion, if you see, you've got one alkyl group. So this CH3 group that you see is one alkyl group that is attached to this carbon containing negative charge. So what happens? This has +I effect. That means it has the tendency to donate the electrons towards this carbon. So in that process, it is going to intensify the negative charge on the carbon atom, thereby making it unstable. Okay? So primary carbanion has got one alkyl group and it is going to be less stable than methyl anion. When talking about secondary carbanion, now as the name suggests, in the secondary carbanion, this carbanion is going to be surrounded by 2 carbon atoms, right? So there are going to be 2 alkyl groups that you see. This is one and this is the other. So the secondary carbanion contains 2 alkyl groups. These 2 groups are going to push their electrons towards this carbanion and thereby increasing the negative charge present on the carbon atom more, and thereby making this less stable than primary carbanion. Okay? So we can see here how they donate their electrons to this carbanion. Then lastly, we have tertiary carbanion. Now here we can see in the tertiary carbanion, there are 3 alkyl groups, 1, 2 and 3. And this tertiary carbanion is less stable than secondary carbanion. Why? Because there are 3 alkyl groups now, and more the number of alkyl groups, more will be the plus I effect. That means more electrons will be pushed to carbon having the negative charge, and thereby the negative charge that the carbon already had, that very charge will get intensified further because there will be more number of electrons that are being pushed towards that carbon atom. So thereby this carbanion will be destabilized. So that is why tertiary carbanion is the least stable among all. So if we talk about the stability order of carbanion, this is the order that is followed. So the stability order is, first will be the methyl anion because it has got no alkyl groups. Then we have primary carbanion, followed by secondary and then tertiary. Now, do you know the stability of carbanion? It can be determined by the following. Stability of carbanion is directly proportional to minus I and inversely proportional to plus I. Now, stability of carbanion is directly proportional to minus M and inversely proportional to plus M. Now, stability of carbanion is directly proportional to resonance. Now what happens in carbanion, the carbon carrying negative charge, it contains one sp3 hybridized orbital that has the lone pair of electrons, right? Now due to the repulsion between the electrons, there is no possibility to undergo bonding interaction with the nearby CH bonds, okay? So hyperconjugation is not at all possible in case of carbanion because that sp3 hybridized orbital, it has got electrons in it. And due to the repulsion between these electrons, there is no possibility of bonding interaction with the nearby CH sigma bonds. Now, when you talk about the order of stability for carbanion, this is the preference order. So minus M effect is given preference over resonance, and then the negative hyperconjugation, and then lastly we have minus I effect that will be considered at the last. So this is the priority order or the preference order that is given when you determine the stability order for carbanion. You have already learned in detail about these effects in the previous lecture. Now let's talk about carbenes. Now what is a carbene? Carbene consists of a neutral carbon atom which has a valence of 2. That is, it is divalent and it has 2 unshared valence electrons. So, neutral divalent carbon species in which the carbon atom is bonded with the 2 atoms or groups, and it contains 2 non-bonding electrons. It is known as carbene. Now, it is also a short-lived species and it is highly reactive. Now, how are carbenes formed? They are basically formed by photolysis or thermolysis or pyrolysis of diazoalkanes or ketenes. We've got diazomethane, and what happens? So here we can see that diazomethane gives methylene carbene and nitrogen gas. So here we can see that this is the CH2 and then we have 2 unshared valence electrons, okay? So this is the carbene. Now when you talk about the hybridization, the carbenes can be sp2 hybridized as well as sp hybridized. Let's take a look at the sp2 hybridized carbenes. Now, there are 2 classes of carbenes, singlet and triplet. Now, basically, these 2 classes, they differ in the electrons spins that they possess. Now, in the singlet carbene, as we can see here, the central carbon is sp2 hybridized, okay? And the 2 sp2 hybridized orbital, what do? They form 2 sigma bonds by overlapping with 1s orbital of the hydrogen atom, as we can see here. So we have got 2 CH sigma bonds, right? But we have one of the unhybridized sp2 orbital, right? So the third sp2 hybridized orbital is going to have the 2 non-bonding electrons. So this is the hybridized sp2 orbitals where it has the 2 non-bonding electrons. Now here you can see that this is the singlet carbene, which is the spin paired. So we can see that the non-bonding electrons here, they are located here and they are paired. So singlet carbenes, they are spin paired, and Singlet carbenes has got no unpaired electron, as we can see here, right? So an empty unhybridized p orbital is present here, which is perpendicular to the plane of sp2 hybridized orbitals. And the two non-bonding electrons, they are paired in this sp2 hybridized orbital. Okay, as we can see here. So singlet carbenes, they are spin paired, and we can see we have got no unpaired electrons here. The total spin here is 0. So we can say that the singlet carbene is dimagnetic as it possesses no unpaired electron. Now let's talk about the triplet carbene. Now what happens in triplet carbene? The total spin here is 1, because the triplet carbenes have got two unpaired electrons. One is in this p orbital and one is in sp2 hybridized orbital. So this is the difference that lies between the singlet and the triplet carbene. Here in the singlet carbene, it is spin paired, but here in the triplet carbenes, they have two unpaired electrons, one here and one here. So the total spin here is 1 plus half giving 1. So this is the triplet carbene, and the triplet carbene is paramagnetic. Why? Because it has the unpaired electrons, as we can see here. So this was about sp2 carbene. Let's take a look at sp carbene. This is the triplet carbene which has the central carbon atom which is sp hybridized. Okay. Now there are two sp hybridized orbitals that are going to form two sigma bonds with the hydrogen atoms, as we can see here. And we are left with two unhybridized p orbitals, right? Because this is sp hybridized. So we are left with two unhybridized p orbitals, right? So what happens? The two unhybridized orbitals, they are perpendicular to each other and they contain one electron each, as we can see here. So this p orbital has got one electron and this p orbital, which is perpendicular, has got one electron. So this triplet carbene has a linear structure because it is sp hybridized, of course, and it behaves as a diradical. Note that triplet carbene is more stable than the singlet carbene. Now let's take a look at the nitrines. Now in nitrines, what happens? Nitrogen has one bond pair, as we can see here, and it has two non-bonding electron pairs. Now these are the neutral monovalent organic species in which nitrogen has a sextate of electrons. What do we mean by sextate of electrons? It means that it has got 6 electrons, as we can see here. 1, 2, 3, 4 and 2 here in this bond pair, which makes 4 plus 2, 6. So nitrines are highly reactive and they can act as a strong electrophile, as they only require one pair of electrons in order to complete their octet. So they serve as strong electrophiles because they want to complete their octet. They are electron seeking. They need 2 electrons more to complete their octet. Alright, so this was all about nitrines. Now this is the structure of benzene. So benzene contains one carbon-carbon triple bond in the benzene ring. Now there is a formation of a weaker new CC bond by sideways overlapping of sp2 hybridized orbitals of two adjacent carbon atoms. So here we have got one carbon atom and this is the another carbon atom. So this is the sp2 hybrid orbital of this carbon atom, and here is one sp2 hybridized orbital of this carbon atom. Now what happens? Sideways overlapping takes place between these two sp2 hybridized orbitals of these two, of course, adjacent carbon atoms, and this gives rise to the new CC bond. Okay, so that is why benzene contains one carbon-carbon triple bond, because of this formation of a weaker new CC bond, which is formed due to the sideways overlapping of sp2 hybridized orbitals of these two adjacent carbon atoms. Now, benzene is a neutral, highly reactive organic species. Okay. So this brings us to the end of this video, where we talked about types of cleavage of a covalent bond and various type of reaction intermediates, where we looked in detail at the types of reaction intermediates, which are free radical, carbocation, carbanion and carbene. That's all for this video. Thank you.